Hello everyone, my name is Kim Sunjae and I am attending Suncheon University as a master degree. The topic for this presentation is precision watering system designed according to the soil condition of crops. Then I will start the presentation. The table of contents is as follows. First, I will briefly explain the abstract. And chapter 2 will explain the structure, configuration, and precision irrigation system, implemental procedure performed in this paper. And chapter 3 is about the implementation process. And after explaining the database and application, which are the elements of this system, we will explain the comparison process for each scenario. Lastly, I would like to conclude. First, I would like to briefly introduce the abstract. It is urgent to prepare measures for efficient irrigation of crops to increase rapidly increasing population and food demand due to climate change. To solve this problem, the system to be proposed consists of 3 scenarios by selecting green onions, one of the target field crops, and IoT sensor and weather agency AWS data are designed in a structure that combines database and mobile application technology. And soil humidity data and temperature data measured by weather agency AWS are shown to users through the application, and irrigation is performed and notified to users. Through this presentation irrigation, it is expected that farmers will be efficient in saving indiscriminate waste of agricultural water, and that it will provide optimized irrigation system convergence to farmers who grow field crops. Due to the rapidly increasing population in recent years, much effort has been made to increase to food demand required for human survival on Earth. In addition, it is urgent to prepare measures for efficient irrigation of crops due to droughts due to climate change such as global warming. To address this problem, precision agriculture, one of the survival cutting-edge technologies that increase productivity, use specific sensors and software to sustain the productivity of crops. As a technology that receives exactly what is needed to optimize the possibility, it is possible to simultaneously monitor crop conditions. Research on the irrigation system for precision agriculture is being conducted in various ways. The irrigation system currently in use has empirical method of managing the timing and amount of irrigation using a timer observing the growth state of a crop, and an automatic irrigation method of controlling the water supply by measuring the water state in real time. In addition, in order to optimally manage the elements necessary for the field crop environments, a system is established to predict the production of the field after big data analysis using IoT such as a soil component collection device. However, we irrigation method that do not fit the characteristics of crops, the condition of the soil and the environment are fatal to crops and can have a great impact, such as an increase in water consumption due to irrigation methods. This paper aims to design and proposes a precision irrigation system for optimal growth by incorporating green onions, one of the crops of field vegetables, into the study while increasing the efficiency of water use according to the characteristic of soil for precision agriculture. In addition, the research result of this paper are expected to contribute to the saving of indiscriminate waste of agricultural water, and farm income can be expected to be improved by providing optimized irrigation system comparisons to farmers who grow field crops. Next, we will explain the system design. Chapter 2. System design. The structure of the study presented in this paper is as follows. First, 3 layers are presented, and the lower physical layer consists of soil moisture sensor and temperature sensors to measure the soil environment, while the middle layer consists of sensor data managers that store measured sensing data in database or deliver it to web servers and mobile application servers. Finally, the top application layer consists of an automatic irrigation system and an abnormal situation notification service. Each service content will be described in detail in the next chapter, implementation. It is the composition of this paper. Prior to entering the composition, we investigated similar research contents, and the most similar research was the FIGAR project, which can be seen as a similar study in that it uses the Internet of Things to improve water quality, productivity, and irrigation methods. Now, to find out the composition of the study conducted in this paper, soil moisture and temperature sensors were used to detect soil moisture and measure field temperature suitable for green onions, which are field vegetable crops. In the case of database, it was built to measure the soil characteristics and data of green onions, which are the target crops in the sensor, stored them in the database and delivered them to the application server and the web server at the same time. Regarding the AWS system of Korea Meteorological Administration, the AWS system was used to automatically deliver real-time weather condition to perform precise irrigation. It is a system that guides use to provide a smooth irrigation system for specific systems, such as irrigation performance guidance and abnormal situation guidance. In the event of an abnormal situation, the user the user may perform repair measure on the part. For the aforementioned guidance, information can be received and used through the PC web or smartphone app delivery service. In this chapter, you can now see the system flowchart for the precise irrigation according to the soil condition of the crops. The order of the automatic irrigation system performed in this paper is as follows. First, it collects weather information from AWS and sensors and measures soil information. Stores in a field database and stores it in a PC web or mobile web server. Based on the analyzed data, the crops is irrigated by the automatic irrigation system, and in the event of an abnormality in irrigation, notification is sent to the user and the automatic irrigation system based on the feedback provided to take action. If it is difficult to repair the automatic water system remotely, it must be repaired manually. Finally, the user adjusts the irrigation cycle by checking the crop status, the number of operation of the automatic irrigation system, and the operation cycle through the mobile application or PC web. This information is stored again in a database to provide an optimal precision irrigation system for crops. The following is an ER diagram for database construction. It is designed to store the date, time, and place of the data measured by environmental sensor in the environmental information table. That is, data on the number of cycle of operations and type of abnormal situations. Finally, it is designed to realize precise irrigation according to the soil condition of crop through analysis from the database containing soil environment data, the number of application, cycle of the automatic irrigation system, and abnormal situation data. This chapter mainly deals with application implementation. First, as shown in the figure, you can check the real-time weather screen conjunction with the Meteorological Administration AWS on the main screen of the automatic water system application, and check the temperature value and soil humidity value measured by the sensors at the bottom. In addition, in the bottom part, you can determine the total number of operations and operation cycle of the automatic irrigation system. And in the event of an abnormal situation, characters about the abnormal situation notification will be displayed in the red space at the bottom. One of the application functions, the setting function, allows remote control of the operating cycle of the automatic water system. And the control function suffers the ability to start and initialize the automatic water system through the remote function in case of an abnormality. In this chapter, a precision irrigation system was installed according to the soil condition of the crop to measure the difference. As mentioned earlier, the target crops were selected as green onions and installed in general vegetable gardens and smart flowerpots and greenhouse in the same area to collect soil humidity information and temperature information and AWS in the Korea Meteorological Administration from August 10 to 23 and 2020. Analysis of visual graphs through three scenarios show that the humidity value and temperature value of the soil were different even if the regions were the same in the case of figure 1. The soil information in the field environments was not significantly different between the temperature and soil humidity on rainy days. Depending on the weather of the Meteorological Administration AW shown below the graph, and the measured temperature and soil humidity were significantly different on clear days, and 12 irrigation was performed. As a shown result of the analysis in the vegetable field, it was observed that as the temperature increased, the soil humidity decreased significantly and the amount of irrigation increased. In figure 2, the humidity value and temperature value of the soil measured from the sensor installed in the smart pot are not affected by the weather compared to the ground environment in figure 1. And automatically controlled temperature and humidity environments are established to maintain in a stable graph, and irrigation was performed 4 times. In the case of figure 3, since the smart greenhouse, soil environment irrigation is not affected by the weather as shown in figure 2. A relatively stable graph was observed and 8 irrigation was conducted. As a result of comparing these 3 scenarios, precision irrigation can be used to build an optimized environment through precision irrigation suitable for field vegetable crops, and introducing this information into the automatic irrigation system is expected to help save water. This is the conclusion of this paper. If the research results conducted in this paper are used in agriculture, it is expected that farmers will save indiscriminate agriculture water waste through precision irrigation and provide convergence to farmers who grow wild vegetables by checking the operation status and real-time water information through applications. In the picture, we plan to develop into a system that processes decisions to users based on the result of irrigation in combination with artificial intelligence technology. Thank you for listening with us, and we will see you with better result next time. Thank you.